I gotta be honest, this morning I was working on my paper, and I break my heart. I'm sorry. I thought someone would kick me, but did I tell you what happened? No, what happened? I told you I saw her and it just sang. It doesn't go, it's literally my height.
You stopped posting. And like a lot of them,
and since my sister was gone and she was there, my mom just made her appetite, so we had her.
Mark doesn't want to get coffee with me. He's a little steady.
Oh my god, I have a job interview.
Not even thinking about it.
Priorities, Matt. Priorities. All I'm hearing is excuses. Amber, did you hear me? Did you hear me? That all I'm hearing is
Okay, so this is what we know. We know that boiling point is a characteristic. For water, that value is 100 degrees Celsius. That melting point or freezing point is a characteristic value. For water, that number is 0 degrees Celsius. And that these were examples of what we've learned to call intensive properties, which means they don't depend on amount. They only depend on the identity of the thing that you're looking at. So if this side of the room has a small beaker of water, this side of the room has a big beaker of water, both of those freeze at 0 degrees Celsius. Doesn't depend on amount, it just depends that they're both water. As long as they're both pure water, then you get the same answer. Intensive property doesn't depend on amount. Okay? And this whole thing about them being an intensive property allows these things to be constant, because it doesn't matter how you design your experiment, on what scale you design your experiment, versus how I design mine. They're going to find the same number. Do it on a different scale with a different electrical heater, and I do mine on a small scale with a flame, we're still going to end up with the same number. Okay, so we have these numbers. They're constants. They're characteristic of the material. How could I change them? We've just set this up to say these numbers don't change. What outside forces could change them? Number one, let's deal with that first. We assume an awful lot from that statement up there, that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius at sea level. At atmospheric pressure it does. That's just taken for granted. That's so much taken for granted that we don't even write it in. But that's the thing. Okay, if we change the outside pressure, it's going to have some bearing on what my experimental values are. It's easier to see for boiling than it is, I think, immediately for freezing, but if you can see one, you can see the other. Here's a liquid. It's a container. It has particles in it. Those particles have a distance between each other so that they're not close packed. that they're allowed movement around each other. They are fluid. I'm going to promote one or more of those liquids into the gas phase, out of the container and into the gas. Now, if you've seen water boil, water's not particularly typical when it comes to its behavior in boiling, but you'll have seen it come to a rolling boil, where when it gets hot, little bubbles form, and then those bubbles dislodge from the inside of the container, and then they rise, and then they become larger and larger, and it kind of churns. That whole churning means that I'm not limited to water molecules that are at the surface anymore. I'm now allowed to promote any of these molecules into the gas phase. So let's pick one. There it is. And this is going to churn around for a while, and then it's going to escape. What do you think the force that's preventing it from escaping actually is? So I'm going to put heat in here. Heat's an energy. Energy is going to be converted from just regular thermal energy into kinetic energy, which is going to allow movement, and then that particle is going to have some kind of force to allow it to leave the container. What force do you think it has to overcome in order for it to leave the container? What force is pushing down in the opposite direction? That's your atmospheric pressure, which you could argue is gravity pulling on all the gas molecules above you, pulling them down to the ground. But what I've got right here is atmospheric pressure. Okay. So this liquid is going to boil when its vapor pressure, really give it enough energy that it carves out a little space for itself and makes itself have a vapor pressure. That liquid boils when its vapor pressure is equal or higher than the force that is preventing it from escaping. Okay. How would we quantify atmospheric pressure? If I had to put a number to it, what number would I assign to atmospheric pressure?
1.
I could give it a 1 and just call that 1 atmosphere, or I could give it some other numbers.
760 millimeters mercury.
Those are the big two. You could say that it's 101,000 pascals. I'm not a fan of the Pascal. Don't know that pascals show up particularly much in our book. Atmospheres lend themselves to simple mathematical solutions better. Okay, so if I can give this sample enough heat that some, remember it's not going to be all of them, some particle now has enough motion to carve out a pressure, which is a force per area, so that it can leave, and it will leave when it can overcome the force that's pressing it back down. Okay, that's what happens during boiling. Now I could change atmospheric pressure one of two ways. I could make it go up, or I could make it go down. Let's have it go up. What happens to the boiling point if I made atmospheric pressure be higher? What would happen? Boiling point would have to go up. If I increase atmospheric pressure, tells me there is now more resistance to boiling. There is more resistance to getting out of the container, which means I now in turn have to try harder. So with increasing pressure, I'm going to increase the boiling temperature. So if I increase pressure, I elevate the boiling point. That one's relatively easy to see, I think. For freezing, it's not quite so simple. Two things happen when you're freezing. First of all, liquid's not particularly compressible. So if I want to see what's happening to the freezing point while I increase the external pressure, I'm not really going to have a very good handle on that, because liquids are not really that compressible, and solids certainly aren't. So this effect is not going to be as easily seen as the transition to a gas. Gas is very, very easily compressible. So a pressure on a gas is going to have an obvious effect. This goes back to where we were before the break. Now here is some ice. Okay. Packed closer together now than they were over here. What happens if you increase the pressure on the ice? What do you think happens to the melting point, the freezing point? This one's more difficult to visualize, I think. Except we've already done it. What if this was a layer of ice and the thing pressing down wasn't just the atmosphere, it was the weight of a person who's wearing ice skates? What did that do to the ice? Remember the phase diagram for water was wrong because this fusion curve tilted the wrong way. Fusion curves normally tilt this way, which means I'm on a kind of slippery slope anyway, because I'm demonstrating now what's going to happen to the most viable candidate for liquid, water. But water's atypical. So this is kind of a odd thing. So this was our phase diagram, right? Solids, liquids, gases. And this was pressure, and that was temperature. And at 1 atmosphere, my line was somewhere there. So this is currently where I am. What What happens when you increase pressure? Move into that place. You liquefy the water underneath the ice skater's feet, which just made it more difficult to freeze. Yes? The ice is frozen. You press down on the ice, it turns into water. You just made it more difficult for the ice to freeze. So elevating pressure elevates the boiling point and depresses the freezing point. Does anybody still cook? I mean, is cooking a thing of the past? Does anybody still, like, does anybody own like a pot and a pan and they regularly source food that's not frozen and go home and cook it and prepare it themselves? All right, okay. So walk me through this. Here's a pan, and it's partly filled with water that we've put on the stove, and we're going to boil because we're going to cook something in the boiling water. What are we cooking today in the boiling water, people who still cook?
Pasta.
Okay. What kind of pasta?
Bow tie pasta.
What are the bow ties called? Are they farfels?
Oh, I thought it was just bow tie pasta.
Those are beautiful bow tie pastas. They have multicolored bow tie pasta too.
Okay.
Oh, I thought we were doing that.
What could how long does it take to cook the bow tie pasta?
10.
Between 9 and 11 minutes. Read the box, please. If your pasta comes delivered to you in a box, it takes 9 to 11 minutes to cook. Who makes their own pasta? Okay. So are you really cooking?
No.
If you buy stuff in a box, yeah, if your food comes from a box, you're approximating cooking, you're not really cooking. No. If you made your own pasta, how long would it take you to cook it?
20.
No, take you less.
Really?
Yeah, like 20 seconds. It's like in, blop, 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 blop,
Oh,
blop, blop, blop,
yeah.
out. Fresh pasta, you just cook it and go.
So you like soft.
I don't know how yeah, al dente. I like my bows al dente.
No.
What simple thing could I do to turn my 11-minute cooking of the farfalle into 9 minutes? Because you know, those 2 minutes I'm going to really use those. What have I got lying around in the kitchen that I could use to make the cooking time be faster? We're going to come back to that answer later. That is not.
Oh, put a lid, yeah.
I could put the lid on the pan. Why?
It keeps the steam in there.
Because then the steam that left the container cannot go anywhere and comes back and pushes down on the liquid. What does that do to the liquid?
Heat it up faster. No.
It's not a question of faster. What just happened to the temperature of the boiling water? It just increased because the pressure inside the pan is now higher than atmospheric pressure. But if you boil this hard, what does it do to the lid of the pan? Yeah, it lifts the lid of the pan to equilibrate back to approximately atmospheric pressure. And what could you do to prevent that happening? You could clamp it down and make a pressure cooker in which the pressure inside here does not get to escape. And now it's pushing down heavily on the contents of the pot. And instead of boiling at 100 degrees Celsius, this is boiling now at much, much higher than that. And now you can cook things that take a long, long time to cook in an abbreviated amount of time. That's why pressure cookers exist. Anybody have a pressure cooker? Does anybody use the pressure cooker?
Mm-hmm.
You use it? What do you cook in your pressure cooker? Rice, it speeds rice up, especially brown rice, because brown rice takes a while to cook. White rice only takes 20 minutes to cook, so I don't bother. What do you cook? You cook meat. You could do a roast in it, right? Hot roast. Okay, so changing the pressure is a way of changing what we've said here, because that has implied in it that we're doing this at 1 atmosphere, at atmospheric pressure. The other thing that we could do to change the boiling temperature of a liquid was, we said it just a minute ago, and I told you to hold your fire.
Oh, salt.
Yeah. The active word here melting point and boiling point are characteristic for pure materials. Water, pure water, boils at 100 degrees Celsius. You add something to it, and it doesn't boil at 100 degrees Celsius anymore. Adding salt to water during your cooking. Adding salt during cooking could have 3 possible purposes. Flavor enhancer. That's a good one. Some kind of nutritional value. If you don't have salt in your diet, that's a bad thing. You need salt, you need sodium to have your neurons fire correctly. Unfortunately for us, modern Western food has far too much salt in it. Too much. We're living in the lap of luxury all the time, and we're paying the price for that. Adding salt to the water for the pasta or for the rice or whatever is not for flavoring. It's not for nutrition, because you're throwing that water away. It's for the third reason. Why are you adding salt to the water? What's the purpose of adding salt to the water while you're cooking? You have to have a purpose or you wouldn't do it. Okay. Here's your container. It contains some water. And Now it contains some sodium chloride.
It's not particularly good. Come on.
Green's on its left. It's not going to be green anymore. It's red.
There's salt. You've added salt to the water. Previously, we picked a molecule of water. It's in the big churning middle of the water, so it's allowed to leave.
Here you go.
There it is. It wants to leave, and while it's trying to, oh, that salt right there, it's in its way. The salt has become an obstacle. It's in the way of the physical process of me, the energetic water molecule, from leaving the container. And look what happens. If I add more salt, what happens to the boiling temperature? Every one of the red dots is an obstacle. The blue dot has to get around in order to leave the container. Are the red dots making it easier or more difficult for the blue dots to leave the container? Which means I probably need more of this then, don't I? So what happens to the boiling temperature when you add salt to the water? Yeah, and what have we decided is the way to express that in words? Use the word elevate for a number that increases. Adding an impurity elevates boiling point. Elevate the boiling point. Okay. And the more that I add, the more effect I see. Right? Okay. So you want to reproduce your cooking round at a family member's house. You go to your granddad's house and you're going to cook your rice and spaghetti and bow tie pasta. It's your specialty. And you go to his pantry to get the salt. And granddad's not allowed to have salt in his diet because he's got a heart condition. He doesn't have salt. He has the iodized salt instead. So instead of sodium chloride, his salt, granddad's salt, is potassium iodide. What happens if you sprinkle potassium iodide into the water instead of sodium chloride? Let me help you visualize that. What happens? Exactly the same thing. Exactly the same thing. This no longer depends on what you are, only how much there is of you. This does not depend on what the identity of the red dot is. The red dot is an obstacle. It only matters, do I have 5 of them? Do I have 500 of them? Do I have 1 of them? The amount of the obstacles is the only thing that matters. The identity doesn't. This is the exact opposite of what we had over here. In an intensive property, it didn't matter how much we had, it only mattered what the identity was. Water, 0 and 100 degrees Celsius. Here, it doesn't matter whether I use potassium iodide or sodium chloride. This is what we call a colligative property. It only depends on amount. Not the identity of the sample. So, adding an impurity elevates boiling point. Let's look and see what happens on the other end of the scale. At some point in the near future, you're going to graduate and people are going to fall over themselves offering you jobs. And some of those jobs are going to be in lesser states than Texas. Some of those jobs were going to be in cold weather states. My advice is consider your lifestyle before accepting any job. But I worked 11 years in Detroit, and Detroit has winters for about 5 months of the year. Remember spring break? Spring break was awesome, right? There's still snow on the ground in Detroit. Snow for a good solid 3-4 weeks after spring break. It's ridiculous. It's just. Remember Halloween? Halloween was cool. The kids go out and they run around from house to house in costume. Well, first of all, they do. In the suburbs around, I don't know what they do in Detroit. Hopefully they do. I know the night before Halloween in Detroit's another matter completely. The kids have to wear an overcoat and a hat and mittens because they can't go trick-or-treating because it's too cold. It's already started snowing. So you can't run from house to house in your costume. And then you got all the ice in your driveway. How'd you make the ice in your driveway go away?
Salt.
You had salt. How'd you make the ice in your granddad's driveway go away? He doesn't have salt. He has potassium iodide.
Put it on.
You add that. Doesn't matter. It doesn't matter what it is that you add, as long as you add something. If you throw salt onto the layer of ice, hopefully you remember this. the water molecules stick to each other through one of these things. What were those things called? That's a hydrogen bond. And the water molecules stick to each other in 3 dimensions through hydrogen bonds. What if there's an obstacle in the way? Then they don't stick. So for every one of these obstacles, now the ice, solid, isn't sticking to the other ice, water, around it. And so now, oh, I can move through that fracture. And now I've got a fluid. Oh, it's a liquid. And then it drains away from the driveway. You throw the salt on the driveway and you make it melt. What does an impurity do to the freezing point of the solid? Do you remember the lab that we did early on where we measured the latent heat of freezing for water in a little test tube? Yeah, you put your thermometer, your temperature probe inside the test tube with distilled water in it. What did you do with that test tube? Put it inside a beaker of water. Ice water. What's the temperature of ice water? 0 degrees Celsius. Is 0 degrees Celsius cold enough to make something else 0 degrees Celsius? No. No, because you have to average the two. If I've got $100 and you've got $50, if we combine our money together, we both have $100, right? No, because I had 100 and you had 50. If we average them together, we've got 150 total, and we get 75. And remember, money is temperature. Temperature is money. It's the same thing. Whatever you can do to money, you can do to temperature. They're really good. They align very well as analogies. So, if I have a test tube and the water in it is at room temperature and I put it into an ice bath and the ice bath is at 0 degrees Celsius, I have no chance of making the water in here go to 0. None. Because all that I can do is average it out. And the average of the big bucket at 0 and the little sample at more than 0 was never going to average to 0. So the temperature in the ice bath needed to be below 0 in order to make the water in that test tube freeze. How did you get the ice to be less than 0? You added salt. How much salt did you add? Quite a lot. And the more you added, the colder it got. Down to the point that you could have the ice water bath be at -4 degrees Celsius. And now that's cold enough to make the heat that's left inside this test tube not evaporate, but like diffuse into the rest of the sample. Okay. So this is going to depress the freezing point. If you live in municipalities like Detroit, they come around and they salt the roads. They have the big trucks and they sprinkle salt on the roads. But they don't do salt everywhere in the world. Some cities don't use salt. What do they use instead? some cities use sand. Detroit doesn't use sand, it uses salt because the sewer system in Detroit cannot handle sand, couldn't handle that much mud. But because salt dissolves, it washes away. But you could sprinkle an impurity. We were not very specific about this impurity. This is just an impurity. If you sprinkle sand on the ice, the sand is an obstacle. It gets in between the pieces of ice and stops them sticking to one another, and then progressively that ice melts. What if you add sand to your granddad's spaghetti? It's going to have some effect. I mean, it's not something that you would want to serve because now you've got sand in your spaghetti, but it would have an effect. The fact that it's non-soluble in water and it goes to the bottom would be a problem, but it's still going to impede boiling and will still have an effect on the temperature. Evaporation is a phase transfer, but it's different from boiling. This is a phase transition that goes from liquid to gas that is not at the boiling point. And again, it's going to be the same kind of diagram. Here's a container, and it contains a liquid. There is a gap between each of those liquid particles, molecules, atoms. Evaporation is a phase transition from a solid into a liquid, but it occurs at a temperature that is not the boiling point. Okay, so this is something you can do at home. If you have a glass of water and you leave it on your nightstand, after a day or two, that glass is empty. Where did the water go? Where did it go? It evaporated. But how could it possibly evaporate? Because the amount of energy that it takes to turn the liquid, I'm pointing at a diagram that doesn't exist anymore, to turn the liquid into a gas was 100 degrees Celsius. Does the thermometer in your apartment go up to 100 degrees Celsius? No, not Celsius. That would be a big number. I'm not going to say what that other number would be. I almost fell into the trap of saying that another scale. So how is it possible that any of these liquid molecules have escaped the container? Because you're not boiling it. Here's how. The amount of energy that it takes to boil this sample, let's just make up a number. To boil this water is going to cost me 100 energy units. Okay? Just made up. But that's to boil all of them all at the same time. Right? If you put this pan on the stove and gave it 100 energy units, then it would come to a boil and you would see the entire sample saying, me, let's go, let's turn into a gas. Big bubbles in the water, of like everything from the inside of the liquid. Me next, I'm going to turn into a gas. What would it cost just to do one of them? Just to turn one of them into a gas. Significantly less than this, because this was for the whole sample. For the whole sample, it's going to cost me 100 degrees Celsius worth of energy. But I'm not asking to do them all. I'm just asking for one of them. What if, instead of 100 degrees Celsius energy, I only had 25 degrees Celsius energy? I only had 25 energy units. 25 energy units, if I distributed it evenly amongst the whole sample, would not be nearly enough to boil them. But if I concentrated all that energy into one atom, one molecule, that would be enough to boil that one molecule. And we've been here before. There's 25 people in the room, and the net worth of the entire classroom is $25. How many permutations are there that one person gets $1? That everybody is a complete free distribution, equal distribution. That can only happen one time. That makes it the least likely outcome. However, it's as equally likely that I have all $25 and you all have nothing. With my $25, I'm heading out of the door. Because it's not really $25 because my sample doesn't really have 25 molecules in it. It has 950 trillion molecules in it, and so instead of $25, it's $960 trillion. And when I win the lottery, I leave town. Evaporation happens below the boiling point because you have an unfair sharing, unequal sharing of energy. One of them gets all the energy, which is enough to overcome the pressure, and they evaporate, they boil at the surface, one at a time. They vaporize. Boiling's not the right word. They vaporize from the surface, one molecule at a time. If the net worth of the room was $25 and I leave the room, what happens to the net worth of the room?
Just for
You become poor. You were already poor, but you didn't know it, because the net worth of the room was 25. What happens to the temperature of the sample when the only hot molecule leaves? The sample that's left behind gets cold. Evaporation causes cooling. When you come out of the shower, you feel cold because you have a layer of water on you. But the body heat causes that water to evaporate, pulling the heat out of the system being your skin. Evaporation causes cool. It's a good thing too. See you on Wednesday.